The other way. PH decreasing will imply that
No.
this on its own thing, or is that the acid?
Just that one's the base, yeah.
And then
This
the
is
excess
this is
or the
just a high.
concentrated hydrogen is the acid.
The acid, this is the acid. This is a base. This is just a hydrogen ion. So
Okay.
yeah. Mhm. Which one? Other way around. Yeah, ask people on your team. You guys got more. You weren't sure? Okay, yeah, this one, the one by itself is always the acid. The one with the hydrogen ion is the base. Yeah. Mhm. Yeah. Okay, so you're sending in A or B for the question I have circled there. When pH decreases, when your homeostasis gets disrupted in a way where your pH goes down, which way does this equation need to move to help you with that situation? Does it move to the right or the left? No, no, yeah. All right, so A or B on that question there. One I have circled, right or left? What happens in response to a decrease in pH? Yeah. How does this equation help us fix that problem of a low pH? All right, we got 40 people. I know there's a lot more than that. Give you about 15 more seconds to send those in. If you haven't sent it in, go ahead and send something in. If you have absolutely no idea, just send something in so you get the points. All right, I got 60 people now. 61, 63, a couple more people brought their clickers today, it looks like. 64, we're just short by 8. Anybody else? Just raise your hand if you didn't send it in yet and you're trying to still. Okay, I think that's everybody then. 65. Okay, we are almost 50-50, 52% A, 48% B. Okay, so we're not sure about this, and that's okay. That's what I thought. So we're all right. So let's start with the first one though. Which one is the acid? A, B, or C? A, we got that. Good. Okay, the acid's always by itself. That's the easiest way to know that with any buffer equation. The acid's always by itself. Okay, and then which one's the base? B, absolutely. The base is always over there with the hydrogen ion in any buffering equation like this. Okay, so now the tougher part, how does this equation kind of move or change to help us deal with a disruption of homeostasis? Okay, first thing to remember is we have all 3 of these components in our blood at all times. This is the most prominent buffering system in our body, outside of our cells in our body. So in our blood, in our what's called our interstitial space, the space around cells. So we have all 3 of those things all the time. We got the acid, we got the base, and we got the hydrogen ions. Okay, so if we have a disruption in pH in that first one where pH decreases, what does that mean for the hydrogen ion concentration? Does it go up or down? Up, right? So when pH goes down, hydrogen ion concentration goes up. Okay, so we got more hydrogen ions now. Okay, and the thing about hydrogen ions is that they bind to stuff, right? And they mess with things, right? So when they, especially our proteins, right? So we got so much of our body's made up of proteins, so many enzymes, so many things that help us drive reactions are made up of proteins. But if we get a bunch of hydrogen ions, too many hydrogen ions sticking to those proteins, they start unfolding and changing shape. The enzymes don't work as well. it'll stimulate pain receptors, kind of messes with us, right? So the body doesn't like that, so it has this system in place to help us deal with that. Okay, so which one of those two, the base or the acid, is good at accepting hydrogen ions? Which one, the base or the acid? The base, right? The base is the hydrogen ion acceptor. Okay, so we know that B needs to help us out with this problem of too low of a pH. Okay, so then when we add an H plus to HCO3 negative, how many H's do we have now? If we started with one and we added one, what do we got? Two. We started with a negative charge and we added something with a positive charge. What do we got now? Neutral. So what does it become? Just becomes this, right? That's it. So that's what I mean by moving it to the left, all right? It moves to the left because it just becomes that acid, right? Because that's all it is, just the chemistry of adding an H to the single H. Now we got two. We started with a negative charge, we added a positive charge to it, so it neutralizes it, right? So we got H2CO3 neutral, okay? Now, some of you may be kind of confused, like, why would we make an acid if the problem was too many hydrogen ions? Anybody think that thought? Yeah, okay, we got a couple people admitting it, maybe. It's a total logical thought, right? But the deal with pH is we're measuring free hydrogen ions, not ones bound to an acid, right? When it's bound to that acid, H2CO3, then it doesn't affect pH because it can't stick to something else because it's stuck to that, right? So that's the whole deal with a weak acid and a weak base is we can move that equation to the left if we need to soak up some more hydrogen ions because we got too many, or we can move it back to the right if we need to let go of some more hydrogen ions and add them to the solution, right? So in this case, we're moving the equation to the left, okay? If pH increases, then what? We don't have enough hydrogen ions, right? We've lost hydrogen ions for some reason. Maybe we've ingested something very alkaline, very basic, so it absorbs some of our hydrogen ions, okay? And so then what happens there is we need to add hydrogen ions to that solution. So which of the two helps us out with that, the acid or the base? The acid. The acid is a proton donator or hydrogen ion donator, right? So in order for it to do that, it just has to let go of the hydrogen ion that it has. So when this one loses an H, it goes this direction, right? Because now it's H1 instead of H2. And since it lost a positive charge, it now has a negative charge, right? So that's all I mean by moving it to the right or to the left, is that it just becomes one thing or the other when we either add a hydrogen ion to it or we subtract one. Okay, go ahead. Because it's neutral when it begins at the H2CO3, but we're not just losing an H, we're losing an H plus. Right? So it lost a positive charge and it was neutral, so now it has a negative charge. Yeah, good question. Yeah. Other questions on that? Okay, and then something we'll get into later is the other side of this equation, which is this. This thing here is called carbonic acid, and it can also dissociate the other direction into CO2 and water. Okay, and so when we're exercising really intensely, like let's say we got to run up. How many people live in Young? Anybody? No, couple. Yeah, a couple living Young. If you got to run up the Young Hall Hill, right? You're going to create some lactic acid because that you're going to need to use that stronger energy system for a short period of time. But when you do that, you make an acid. You increase your hydrogen ion concentration. So you're adding a bunch of these, right? Which pushes the equation this way, which then it can push it this direction too, and we breathe out a bunch of CO2, right? That's what it does. That's partially responsible for the CO2 we're breathing out, is from buffering that acid, buffering those hydrogen ions, okay? So where does it go? We breathe it out. Okay, we'll get back to more of that next semester when we talk about the respiratory system, but that's just a kind of a little extra info there. Yeah, go ahead. Did you have your hand up? No. Okay, sorry. All right. Other questions on that? Okay. All right. What I would recommend is just practice that. Have a buffering equation like that in front of you. Practice it. Walk through those steps like I just did with you, because I don't expect you just to be like, yeah, it goes to the left or it goes to the right. You got to walk through the steps, right? Which one's the acid? Okay. The problem: too many hydrogen ions, not enough. Which one helps us with adding or subtracting hydrogen ions? You got to just walk yourself through the process, and it should make sense. But yeah, I know that's a tougher concept. Okay, I'm going to pull up the next set of notes here. Give me one sec to do that. Okay, starting out this one with just a verse that I love that is from Romans 1:20. It says, "For since the creation of the world, God's invisible qualities, right, his eternal power, his divine nature have clearly been seen, being understood from what has been made, so that people are without excuse." So it's just this idea that we can learn something about God from studying what God made, right? The human body. It's a great opportunity to dive into understanding a little bit more about who God is by studying one of the amazing parts of God's creation, which is us, right? And so that's what we get to do in this class. So, okay. Today we're going to talk about chemical bonds, reactions, water, a little bit of kind of intro to chemistry. Okay, but let's start off with just a couple quick review questions from the stuff we talked about last time. So go ahead, talk with the people around you for a second on your team, and give me an answer here in about 45 seconds or so.
Let's go with zeros. Yeah.
But then, no, yeah, well, it's like, it's moved, I know, I have one over. Yeah. Yeah. She's cool.
All right, go ahead and send in your answer if you haven't yet. Give me about 5 more seconds. It's about 10 more of you that need to send it in, it looks like. Good, we got pretty much everybody. Oh, good, we're up to 66, 67. Almost got everybody. All right, good. Everybody, well, 99% of you said E, so both B and C. All right, so we got 1 times 10 to the negative 9th, or we can count 9 places over, right? I'm trusting you that there's 9 there, okay? You got it. Good, okay. What about this one? Let's do this one quickly as well. Let me open the clickers back up. Go ahead. Check with the people next to you for a sec and send in that answer.
Plus ions. Right, right. Yeah.
All right, about 15 seconds. About 20 more of you need to send it in. All right, about 10 more of you, it looks like. Maybe about 5 seconds. All right, anybody else? Okay, 80% of you are saying D, both A and B. So a pH of 2 is definitely more acidic than a pH of 8 because it's that negative portion of the scale. And then it has 10 times more hydrogen ions than a pH of 3. Both those are true. So D is the answer. Okay, questions on any of those? Okay. All right, well, let's jump into just a quick review of atomic structure. I was going to say anatomic structure. That's not it, but you guys are talking about anatomical terms in lab, but atomic structure here. So take a second with the people on your team again and just kind of think about these questions for each of these 3, okay? Go ahead, take maybe a minute or 2, talk about those things, just a quick review, see what you remember from high school chemistry. Go for it.
I'm wondering what you mean. It's like, how much? Yeah, I'm assuming it's one. It's small enough. Yeah. Electrical charge. Involving bonds. Yeah, I think actually it's only electron. Where,
Did you take the
All right, how we doing? We got this? Okay, let's walk through this. So let's start with the density ones. Which ones are known to be not dense at all? Electrons, right? So not dense. And then protons and neutrons are definitely more dense. Okay. All right, what about the electrical charge? Protons are what? Positive, neutrons, neutral, and electrons, negative. Okay. Where do we find protons as far as the structure of an atom goes? In the nucleus. Okay. What about neutrons? Nucleus, so both there for those. Okay. And then what about electrons? Out in the shell, right? Out on the electron shell, so on the outside. Okay. And which ones are involved in bonds, in bonding, chemical bonding? Electrons, right? Yeah, for sure. So just the electrons. Okay. Questions on that at all? All right. Okay. So let's just look at a couple of these models here, right? Some different ways to kind of visualize atoms, right? So looking at the nucleus here in the middle with the electrons kind of floating around on the outside, as well as this electron cloud model where the electrons are just kind of spending their time somewhere out there around the nucleus, okay? Just different ways to look at that. So let's talk about electrons here. Okay, so electron shells are the places that electrons spend their time, okay? And they kind of form this cloud around the nucleus, okay? The first layer of that, the first electron shell, holds how many electrons when it's full? Two. You guys got that for sure. Just 2 electrons there. But then all the other ones beyond that first one, how many can they hold? 8. You guys got that. See, even though you had COVID chemistry, you remember some stuff, right? How many people had chemistry during COVID? Yeah, it's a lie. I know you guys are the COVID chemistry group for sure. That made it harder for sure, but you remember some stuff. You do. Okay, so then we can have up to 7 shells. Okay. And the valence shell is just the most exterior one or the last one in each atom, right? Okay, so whatever the outer shell is. Okay, and so generally we use this octet rule, which means that a valence shell fills up when it has 8 electrons in it, right? And this is going to help us with figuring out bonds, right? Again, except for that one, except for the first shell, which only has 2. Okay, but as electrons move out, then the less tightly bound they are to the nucleus, because the nucleus is, either it has some of the protons in it with that positive charge, okay? And so that's going to attract the electrons towards it, but the further out we get, then the more likely those electrons are to bind to other things, okay? So the more potential energy for those atoms to react with other things, okay? All right, well, let's talk about the different types of bonds that we can have, okay? So number 1 is called an ionic bond. Okay, with an ionic bonding situation, there's 2 steps involved in the process, okay? So first of all, there's a transfer of an electron or more from one atom to another, okay? And so this is the most common situation, sodium chloride, right? This is table salt, right? So sodium only has 1 electron in its valence shell. Chlorine has 7, right? So chloride is pretty much ready just to take 1 more electron to be full. If sodium gets rid of that 1, then it's full, okay? Its valence shell is full. So then we get 1 electron donated here. This one now just took on 1 more electron, so it's negatively charged. This one lost an electron, so it's positively charged. And now these are going to stick to each other, right? So it's a two-step process with ionic bonds, right? One electron goes from one to the other. Now they're opposite charges, so then they stick to each other. So that's the ionic bond. Okay, these are typically salts, right? Salts and minerals a lot of times have these ionic bonds holding them together. Okay, questions on that? Okay, so ionic bonds, and then we get into covalent bonds. Okay, so the defining feature of covalent bonds is sharing of electrons. There's no transfer of electrons, okay, but there's just sharing, right? So we can have single covalent bonds, double or triple. Okay, in a single covalent bond, we have one electron shared between two atoms. In a double covalent bond, it's two electrons shared between the two atoms. Triple, it's three, right? So this example here of methane, right here. All right, so we have a carbon in the middle. How many electrons does carbon have in its valence shell? 4, right? So it's kind of like right in the middle of being empty and being full, right? And so it needs to have 4 more added to it to be full. Hydrogen only has 1 electron, so it needs, and that's only its first shell, right? So it just needs 1 more to be added to it to be full. So 4 hydrogens come around that carbon. Each of the hydrogens shares 1 of the carbons, and then the carbon gets to share all 4 of those electrons, and they're all full. They're all happy, right? And that's so that's 4 different single covalent bonds in that example. Okay, oxygen, O2 molecules. Oxygen has 6 in its valence shell, right? So it needs 2 to be full, right? So 2 electrons are shared there between both, gets it up to 8, right? And that's an O2 molecule, right? Nitrogen gas needs 3 for its valence shell to be full. So all 3 of those electrons are shared between the 2, and that's the triple covalent bond. Okay, questions on that one? Covalent bonds are much stronger than ionic bonds and stronger than hydrogen bonds we'll talk about in a second. So covalent bonds are definitely the strongest. And it usually takes an enzyme or some kind of stronger chemical reaction to form those or to break those types of bonds. Okay, so when we get into, this is kind of a subcategory of covalent bonds. Okay, so we're still talking about covalent bonds, but we need to break up covalent bonds into polar covalent bonds and non-polar covalent bonds. Okay, so there's still electron sharing involved, but when we talk about a polar covalent bond, we're talking about unequal sharing of electrons. Okay, so when we have a situation like water, which is the one we'll spend a lot of time talking about today, the oxygen is just much, much bigger than the hydrogen, has a much stronger pull on the electrons because of its size and because of its all the extra protons within it. And so the electrons end up spending a lot more time on the oxygen side than they do on the hydrogen side. So we end up with this negative charge over here on the oxygen side. Actually, this is the one that shows it, negative over here, and then positive over here on the hydrogen side. Okay, so the molecule itself is still formed by covalent bonds, but the electrons just spend more time on one side of the molecule than they do on the other. So that one side of the molecule tends to be negatively charged, whereas the other side is positively charged. So that's still sharing, but sharing unequally. So it's a polar covalent bond. Okay. Yeah, so that's polar covalent bonds. And then non-polar covalent bonds is the opposite. We equally share electrons, right? The atoms are similar size, similar charge, and so then they share those electrons equally, and it doesn't have a charge within it, right? It's just kind of neutral throughout. Okay, questions on that? So we got ionic bonds, giving of an electron creates opposite charge, then they stick to each other. We got covalent bonds where they share electrons. Polar covalent bonds specifically means they share them unequally. Non-polar means they share them equally. Okay, and then the third type of bond we'll talk about is hydrogen bonds. Okay, hydrogen bonds occur primarily after we already have polar covalent bonds in place. Okay, so we got the positive side of one polar molecule sticks to the negative side of another polar molecule. Okay, so water is the best example of this, right? So we see water molecules here. We see the oxygen part there, which is negatively charged, sticking to the hydrogen part there, which is positively charged, right? So these create little bonds with each other. They're not super strong, but they hold things together. Okay, these have some of the most important significance in all of organic chemistry. because these are responsible for most of the protein shapes that we have. These are responsible for all of the special properties of water that we're going to talk about in a second. And so these polar, or these hydrogen bonds that are created because of polar covalent bonds are extremely important in biology. Okay. One of the examples of what this causes is surface tension in the water, right? When you see this drop of blood coming out, blood is, at least half water, a little bit more than half water. And so the water molecules are sticking to each other when that drop is hanging off of the needle, right? And so that's why it's kind of creates that drop before it actually falls. It creates enough weight. When you get enough of it out there, then the hydrogen bonds can break, but they stick to each other for a bit first. And that's why it kind of turns into that drop first. Okay, we'll talk about those properties more here in a second. Any questions on that? Okay. All right, so just a brief bit of info on chemical reactions. Okay, so chemical reaction is any process that forms or breaks one of these chemical bonds that we were just talking about. Okay, there's two primary types of chemical reactions. One type would be we take two smaller things, put them together and make a bigger thing, right? That's a synthesis reaction. Okay, when we talk about synthesizing something, that means we're making something larger from something smaller. Okay, but then there's decomposition reactions, which are the opposite of that. We take a molecule that's multiple things already, but they're all put together, and then we break that apart and make make multiple smaller things. Okay, so a couple examples. Glucose molecules, which we'll talk about glucose later on. Glucose is our primary monosaccharide, primary carbohydrate in our blood, right? Our blood sugar. Okay, those can be put together. A bunch of those can be put together to form what's called glycogen, right? Glycogen is a polysaccharide, bunch of sugars all strung together. It's our primary stored source of fuel in the body. We store a bunch of glycogen in our muscle and our liver, and we can break that down later to make blood sugar. Okay, so putting those together is a synthesis reaction. But then when we want to get at that glycogen later because our blood sugar is dropping, then the liver will break that down. That's a decomposition reaction. It can turn it back into glucose and release that into the blood. Okay, so the synthesis one is forming glycogen. Decomposition is breaking down glycogen. I don't know if I told you guys yesterday, but if I write something and you just have no idea what I wrote because my handwriting's terrible, I'm not offended if you ask that question at all. So please ask. I understand my handwriting's not good. Okay. Other questions on this at all? Okay. All right. So let's talk about water. We'll spend really the rest of the time here talking about these properties of water. Okay. One thing to note about the special properties of water is this. They're all due to hydrogen bonds that are forming between water molecules, or in some cases, between water and something else. Okay. So the first two properties of water are here. Number one is called high heat capacity. Okay. Definition of that is right here. What that means, it takes a lot of energy to change the temperature of water compared to other substances. Okay. So lots of energy needs to be absorbed before the temperature changes. So a good example of this is a coastal climate versus a desert climate. Okay. Do we have any Arizona people out here? Got some, yeah, Phoenix. Where are you from? Yeah. Goodyear. Okay, yeah. So West Phoenix, right? Yeah, yeah. So maybe help me here with a typical swing in temperature. I know summer it stays pretty hot, but maybe like fall, spring, like when you get those days where it might get pretty chilly at night and then pretty warm. What might be like an average low when you have a big swing in temperature, average low versus an average high?
It'd be like maybe like 55.
55. Okay.
60,
Okay.
midday, like 70.
Yeah, so maybe a 30-degree temperature swing, for sure. That's a pretty common one, right? Sometimes you can even have 40-degree temperature swings, right? Somebody pull out their weather app right now on their phone. I know you told you not to have your phones out, but let's see the high and the low in San Diego today, right here where you're at. 68. So we have a 7-degree temperature swing here, right? And that's pretty common for San Diego, right? But in places like the desert, Phoenix, other places like that, it's common to have a 20 to 40-degree swing, right? It's because of water, right? There's way more water in the air here than there is in the desert, okay? And water is hard to change the temperature of. It takes a lot of energy to change the temperature of it. So we have water in the air, but we also have this giant cooler next to us over there called the Pacific Ocean, right? And there's a lot of water over there. And those things are keeping the temperature here very, very consistent, right? Compared to much drier climate where you don't have a big body of water next to you and there's not much water in the air, temperature changes more. And this is all because of what temperature is, right? Temperature is just how fast molecules are moving, right? That's all it is, just kind of the energy within a substance, right? So when we warm up water, what we're doing is we're just making those water molecules move faster and faster and faster and faster. When it boils, that they finally like break apart and go up into the air, right? And so with hydrogen bonds, they stick to each other, so it's harder to get them moving faster, right? And that's why water is harder to warm up than other substances that aren't polar and aren't sticking to each other. Okay, does that one make sense? Okay. All right. The other good example of this is thermoregulation, which just means the way that we control our body temperature. Okay, the number one way that humans can control their body temperature is what? What do we do when we start getting hot? We start sweating, right? And that's actually pretty unique across the animal kingdom. Most animals, like four-legged animals like, deer and gazelle and elk and all those types of things, they don't have sweat glands like we do. They have little sweat glands that we also have called apocrine sweat glands. Those are the ones that make us stink, right? Body odor ones. They have those same ones, but they don't have the other ones called eccrine sweat glands like we do. We have around 2.5 or 3 million of those in our body, and they just pump out water like crazy, right? And so the reason this is kind of helpful for us is that, well, a couple of things. Most of our body's made of water, right? We have like 66% water, right? So we stay pretty naturally, our body temperature doesn't change much, right? So that's kind of thermoregulation piece. And then this part, if we go into the next property, which is high heat of vaporization, that gets at the sweating thing that I was talking about, which is it takes a lot of energy to take water from its liquid state into its gas state. Okay. And so when we sweat, that's what we have to do to make it effective. We put a little drop of water on our skin. If that drop of water falls off and hits the ground, it didn't help us at all. It just wasted that water. What we needed to do is we needed to turn into vapor on our skin, because then the energy to do that came from our bodies, right? So then that helps us cool down, right? We add energy to that water from our body, and it goes from liquid to gas, and that takes energy out of our body, that cools us down, right? So that's the whole point of sweating, is turning water from liquid to vapor. Okay, questions on that? Go ahead.
I look at like the heat capacity of like coastal climate versus the desert impact, basically like how much the body's internal temperature when exercising, or like how much you're able to sweat when exercising.
Yeah, so you're saying like if you're in a coastal climate versus like a humid climate versus a dry climate when you're exercising. Yeah, for sure. So when you're in a humid environment, it's much harder to cool to stay cool, for sure, because there's already a lot of liquid in the air, and so it's harder to push liquid into the air from your skin. And so there's different constants you can look at that you can measure the humidity and then see how much energy it'll take to actually create to get that water to turn from liquid to vapor. And it takes more energy to do that if there's already a lot of water in the air. It's kind of just like a diffusion type thing, right? There's already a higher concentration of water in the air, so it takes more energy to push it into the air. So when we're humid, or when we're in a humid environment exercising, a lot of the sweat just falls off of us, right? And that doesn't really help us. It just wastes water. So yeah, it's much easier to sweat. We're much more effective at sweating when we're in a dry climate, for sure. Yeah, great question. Yeah. One other application of the sweating piece is that there's certain tribes in Africa that do a type of hunting called subsistence hunting, and pretty much they take advantage of the fact that animals, like I was talking about, like elk and antelope, don't have sweat glands like we do. Those animals are way faster than humans, right? But they can't run for as long, right? And so the hunters would just kind of keep a steady pace and follow these animals for hours and hours at a time until eventually that animal collapses of heat stroke because it can't cool its body down. but the humans can just keep cruising at that pace, even though the animals are much faster than them in a sprinting type fashion, right? And they're just really taking advantage of that adaptation that humans have, which is we're really good at cooling ourselves down. We're really good at sweating. So yeah. Any questions on that? Okay. All right. So those are the first two properties. The third property of water is the fact that it's the universal solvent. Okay. So a solvent is part of a solution. We'll talk about that a little bit more next class, but a solution includes solvent and solute, right? So the solvent is kind of the liquid part. Solute is the other stuff, the particles in the solution. Okay. But water is the universal solvent. Pretty much all reactions in biology and in chemistry happen in the presence of water, right? Because water is really good at pulling things apart. Okay. All reactions are wet reactions. Because of water's polarity, it can pull apart ionically bound molecules. Okay, that's you put sodium chloride into water, and the positive part of the water will stick to the negative part of the on the chloride side. Negative part of another water molecule will stick to the other side of that, and since it's moving, it just pulls it right apart, right? And so it can do that with ionic substances, and it can also do that with polar substances. And so it breaks down everything in such a way that then everything can touch each other and react, right? And that's really what it does as a solvent. Okay, so it dissolves ionic substances, most polar substances, but when it comes to non-polar things like lipids, it doesn't dissolve those very well, right? You know, when you put oil and water together, they just completely separate, right? So it's a non-polar substance. Okay, so we got two other properties here, and they're called cohesion and adhesion. Okay, adhesion means that water sticks to things that aren't itself. Okay, sticks to things, not just water, but they're sticking to other things. And then cohesion means that water sticks to itself. So take a second here, look at these four images, and yeah, decide as your team one of them that represents adhesion. Okay, and talk about all four of them, but I'm going to have you send in on your clickers one of them that represents adhesion. Okay, and turn around and talk to the people on your team, guys, not just the person next to you. Just get in the habit of turning around and talking to each other.
Which one are you asking?
So adhesion. Yeah.
Do you post like your version of the?
Not the ones I wrote on, but the video. That's why I have this microphone on. It's because yeah, I'll post a video.
Like packet is on back order.
Yeah.
I'm not sure, but he said he got his today, so
Okay,
I'm gonna
so
go
maybe
check
go get it.
later
Yeah.
and see if I can find my friend.
For sure. Well, the video is really just the screen and then my voice, so you'll see everything by watching the video.
Okay.
Yeah.
I'm supposed to click it in?
Yeah, just one of the adhesion ones. Yeah.
See on the left, I know. Oh, well. I see that with a lot of this.
This is okay. This is actually one of my favorites. He got confused and for like 3 years.
All right, so you're sending in one that is showing adhesion there. That's what I want you to send on your clickers, okay? All right, about 10 more people, it looks like. Go ahead and send in your answer if you haven't yet. So just one of those that represents adhesion. All right, looks like we got just about everybody. So 58% of you are saying B, and we got 24% saying D, some saying A, a couple saying C, but the majority are saying B. But let's talk about each one of these separately. Okay, so first one, this one here with the test tubes, right? How many people here are saying adhesion? Just raise your hand here. How many people thought that one represents some adhesion? Okay, we got a couple. How many people thought cohesion? Okay, so adhesion is going to be sticking to something else, right? So we're adding something to that substance. Okay, glass tends to have a negative charge to it, and so the positive side of those water molecules can stick to the glass, but just around the outside, right? And then the rest of it sags down, right? And that's kind of what we're seeing there. It's called like a meniscus, where the outside is sticking to the glass and the rest of it's sagging where it's not touching the glass, right? And that's adhesion for sure. That one's adhesion. Of course, there's always cohesion going on anytime you have water, because water's always sticking to itself, but you can't necessarily see the cohesion here, right? Okay. What about B? We got the spider web with a lot of water drops on it. Okay. How many people thought adhesion for this one? This is the one that like 50% of you said yes. Okay. Yeah. Ethan, what do we have? What's going on? Why is it adhesion? Perfect. Water sticking to the web, right? Absolutely. So we got water sticking to the web. Did anybody see this one and think there's some cohesion going on too that you could see? Yeah. Why'd you think?
Because the water droplets are quick sticking together to form bigger droplets.
Yeah, to form those droplets, right? They kind of form that like bead look, and that's the water sticking to itself for sure. So that's cohesion as well. So we got both add and cohesion here. Okay, good. What about the water strider here? What do we think? Cohesion, adhesion? Cohesion for sure. Yeah. So that's surface tension, right? The water strider, the way that it distributes its weight with those long feet doesn't create enough pressure to break the hydrogen bonds between the water molecules, right? So it can just sit right on it. Okay. So that one's definitely cohesion. And then what do we got with D? What do you guys think there? Yeah, we see some cohesion because it's kind of beating up. It's almost like the grass is kind of like waterproof, right? When you have like a waterproof material, it kind of just beads up on that material. Doesn't really stick to the material itself, but it sticks to itself better than it does to the material itself. So that one definitely looks a little bit more like cohesion for sure. Okay, questions on those? Go ahead, Julie.
Aren't they all kind of examples of both?
Sure, yeah, because there's always, anytime you got water, it's cohesing, right? But it's kind of more of like, what can you see going on, right? But totally, there's always cohesion happening. Adhesion, not necessarily, we can't necessarily see adhesion in all of these, but cohesion we definitely can. Yeah, good question. Other question? Okay, another clicker question here. Go ahead, talk about this one with your team. What makes water have so many of these special properties? Yeah.
It's this one adhesion because it's sticking to the
Sticking to the glass, yeah.
Okay.
Mhm.
So water in glass is adhesion because it sticks.
Yeah, just on the sides, like where it's touching the glass. And that's why it kind of like sags down in the middle, because that part's not touching any glass. That makes sense. How it's like kind of goes down, you know? So it's like the outside, all around the outside sticking, but the inside's not touching the glass, right? It's just hanging there. Yeah. So, yeah. Yeah. All right, about 15 more seconds or so. Make sure everybody on your team is kind of in agreement on this answer. Like you guys to talk about this. Okay, I think about 5 more people need to send it in still. Go ahead and send something in. Okay, good. So we have 85% of you saying C. Okay, so hydrogen bonds between water molecules. Okay, for sure. And then if you could have put more than one answer, would anybody have put more than one answer? What would be the other answer? Go ahead. Saw your hand come up.
I would have picked yes, well with that.
You said B? Yeah, the polar covalent bonds within water molecules. Absolutely, right? Because we've got, that has to happen first, really, right? We have to have polar covalent bonds within the water molecules first, and then they can create hydrogen bonds with each other. That's kind of between water molecules, right? So just get used to that terminology of within a molecule versus between a molecule, between molecules there. Okay, does that make sense? Great, okay. All right, and then lastly, I want you just to kind of compare and contrast these two properties that seem very similar with the people on your team and answer these questions together. We'll come back together in about a minute or so. Go ahead.
We had to do both things.
No, I ordered the textbook, but it's on back order. So right now I'm just here. That's.
Yeah, that's fine. Yeah, for sure. Thanks for letting me know. I think somebody said they stopped by today and they had some more, so maybe, I don't know if you've tried today, but yeah, maybe just check it out, yeah.
So, and this one is just saying things different. So have your microphone on?
I do, yeah. I know, so it's weird. People don't want to talk to me when I'm walking around because then you're on the video. It does, yeah. Yeah, exactly. Yeah. All right, let's go ahead and come back together here. So, anybody want to answer this? Are these two the same thing? How do you explain they're different? Anybody want to go for it? Yeah, go ahead.
I said high heat capacity doesn't want to change. Water doesn't want to change temperature.
Okay,
And high heat vaporization is at higher temperatures. It doesn't want to change states.
okay. I like that. I like that. Anybody else want to add anything to that? Go ahead, Hector.
So if they are related, because you have to have high heat in order to have vaporization. You can change water by 1 degree,
Mhm.
and that's high heat capacity, but at a certain degree, much higher on further down, then it's high heat vaporization. So
Yeah.
they are related, but you have to go high heat first and then high heat vaporization.
Yeah, I like that. Yeah, they're definitely related, right? It takes a lot of energy to change the temperature of water, whether that temperature is low or high. So it's kind of like the vaporization one is just a little bit more specifically talking about when the temperature is already really high, close to the boiling point, then it still takes a lot of energy to do that too, right? So yeah, absolutely. They're related, not exactly the same thing. Vaporization, maybe just a little bit more specific than high heat capacity. Okay, any questions on that? Okay, let me just point out a couple things to you guys on Canvas that I want to make sure you're aware of. Okay, yeah. First of all, again, when you click on a lecture quiz like this one, I have lecture quiz 1 pulled up. You can always see what it's over. Okay, so it's over the first set of notes, this one, and chemical bonds, reactions, and water notes. Okay, so it's over the first 2 that we did. You can do that with all of them. Okay, and then I also wanted to show you. If you go to the modules page and you go to the very top, this up here, this course orientation, right here under office hours, okay, you can click on that. If you click on that link, it's probably going to be weird on my iPad if I try to do that, but it might kind of work. No, I didn't think so. But pretty much that gives you, takes you right to my Google Calendar, and I have a bunch of office hours in those slots. And you can sign up for office hours. You can come ask me questions about the class. Okay, hold on one sec. Don't pack everything up yet, because then other people can't hear. Okay. Yeah, and so you can come meet me in my office during those times, and then typically I'll have times on there that are like on the shuttle too. I mean, I usually ride the shuttle. This afternoon I'm not taking the shuttle back, but for the most part, you don't even have to sign up. If you're just sitting by me and you want to chat about class, that's great, or whatever you want to chat about. But I'm typically riding the shuttle both directions, and so we can talk then. I'm also typically here. I usually take the 1240 shuttle, except on Wednesdays I don't, but Mondays and Fridays I do. So I'm here beforehand if you want to come chat about stuff before that. But yeah, I want to be available to help you Emerson, do you have a question?
So will the quizzes, the lecture quizzes on Friday always be about the Monday, Wednesday?
Not necessarily. Sometimes they're over sometimes they are over the Friday one as well, but not usually. But every once in a while that is the case. So sometimes you got to wait till Friday's class is over to take it. But yeah, other questions on that, you guys? Okay, well, have a great time in lab for those of you that haven't been there yet, and we'll see you guys on Friday.